parts about different control devices. Of course, when we started with electricity, we needed to have the ability to control it, right? You understand that? The first basic control devices, of course, we had was switches, and they're still widely used today. Just look at your house and you see they're all over the place. But who controls switches? Well, you control switches. So you have to manually go up there and flip switches to turn loads on and off, right? You understand? Eventually they realized that we could do this with these devices right here we call relays. Now this is only one picture. These comes in all shapes and sizes. But what we do with a relay is basically a magnetic field that pulls a contact, so it makes a contact with a magnetic field. So it uses electromagnetics. But now instead of me doing the control, we can control these devices electrically, right? And then these devices can control the other electrical devices, and now all of a sudden I could come out of the picture, right? So I could set up automated systems now where I come in, I flip a switch, and these relays come in and energize circuits and cause things to happen. But these are not what we consider to be solid state. These are electromechanical devices. Now your car is an electromechanical device, and what's the problem with electromechanical devices? Well, now you got two things that can fail, right? You understand? They can fail electrically or they can fail mechanically. So that's the problem we have with relays. Even though they're widely used today using high current applications, a lot of the stuff is moved over to devices that have no moving parts. The first devices were these things we call vacuum tubes, which are really, really neat. These work in a vacuum, and they work on the principle of attraction and repelling of magnetic fields. In atoms, we know that electrons have negative charges, right? You understand? And then negative charges are attracted to positive charges. So what we do on a vacuum tube is we have an element in there we call the cathode that we heat up, and it's made out of material that when you heat it up, it releases a cloud of electrons. And then we have another unit in there we call a plate, and it's positive charge. Now what's them electrons over here going to do when it sees this big positive over here? They're going to go flying through that vacuum over to that plate, right? You understand? Then what we do is we put what we call grids in there, where we put these little negative potentials real close to the cathode, and now we can control the flow of electrons between the cathode and the plate. So this is where we started getting amplifiers. This is where we started getting digital aspects. But we're now, instead of controlling these electrically, we're controlling them electronically, right? Of course, the problem is they got glass, you know, in them. When we drop them, we break them. They pop every once in a while. And to make these things work, they require a pretty high voltage. So on the anodes, usually they're running around 200 volts up there. So, and they get hot, so they consume energy to work. Because to make the cathode work, we have to heat it up with a heater. Okay, y'all understand that? But they were not. We don't call them solid state, but they were. They had no moving parts. Then we moved into these guys, which we do call solid state. These are what we call transistors. These have no grids. We don't have to heat them up to make them work. But these are the guys. So these are valves. Everybody understand valves. So tubes are that too. Tubes are valves. Y'all know how valves work? What do we use that? What do we use valves for? Huh? To control the flow. Now normally we run into valves every day, but we're controlling the flow of water, right? You understand? What can we do with those valves? Well, with those valves, we can either turn that flow on or turn it off, which that would be digital, right? You understand? Or we can control the flow of the water. Well, that's what tubes do. Vacuum tubes and transistors control the flow of electrons, or control the flow of current, but we do the same thing. But here we're electronically controlling that, right? You understand that? We're not controlling this with a switch, and we're not controlling it in other ways. We're electronically controlling the size of these valves. So we have the ability to open the valve and let current flow more freely, or close the valve and shut the current off completely, right? And then they realized, of course, the size of the valve is dependent on how much flow you're going to control. So the more current we're going to have to control, the more flow of current we're going to have to control, or the more amps is what we rate current flow in, right? Amps. Then the bigger the valve's going to have to be. Well, what if you don't have to control a lot of flow? Well, the smaller the valve could be. So what this allowed us to do is in circuits like computers and stuff like that, where we're dealing with logic or ones and zeros, those ones and zeros can be represented with almost no current at all, because we usually use voltage levels, which means the size of the valves could become extremely small, which means now instead of putting one valve on a wafer, we can put thousands of them, and we put entire circuits on a single wafer inside a single package, and we refer to these as integrated circuits. So these integrated circuits is just made up of thousands or even millions of these devices over there, but they're so small because they don't have to provide the current, they're not actually providing hardly any current at all. So this is basically the succession of what we do. So in digital, you'll learn about these guys. Now the problem with these guys is they can't handle a lot of power. So that means if I need to handle a lot of power, then I'm probably going to have to still have these, right? You understand that? So if you go and look at the output, if you got a power amp in your car, and you look at it, you got these guys in there that's actually driving the speakers. Because I can't get these guys big enough to do that, right? And then, of course, if you want extremely high power, then odds are you're going to move back to these guys. So vacuum tubes are still over there. A lot of people, I'll say this, and they say, well, you can't get vacuum tubes anymore, and that's not true. Just search for them on the internet, because we was talking about the other day, they're really, really popular, high-powered audio equipment, and also a lot of guitar players like to use vacuum tubes because they have a different sound. They don't sound as electronic or crisp. They mellow out. Tubes mellow out, you're saying. So with semiconductors, these are solid substances, usually silicon and germanium, that has a conductivity between an insulator and a conductor. They're right in the center, and that's why they got the name what? Semiconductor. So what's a conductor? Well, a conductor is considered to allow current to flow easy, right? It has very little opposition. An insulator has an extremely high opposition. And a semiconductor is where? Right in the center. And that's how it's got its name. The two by far the most popular is silicon, followed by germanium. But when we get into our like light emitting diodes and stuff like that, they move into gallium. So there's a lot of semiconductors out there, but those are the most popular. What we do is we take the semiconductor and they do something called doping, which we'll look at as we go through our process. Is a process of adding small percentages of foreign atoms into the semiconductor. And once this is done, once the semiconductor is doped, it changes the electrical characteristics of the semiconductor. But what's nice about this is that we can change the opposition electronically. We can control these guys electronically. So I can electronically increase the opposition of the valve, or I can electronically decrease the opposition of the valve. But this is through a process called doping that we'll look at. And of course, solid state, which is what y'all's taking, is referred to electronic components, devices, and systems based entirely on what? Doped semiconductors. Solid state devices operate off of DC. So your cell phone is a solid state device. It operates off of DC. Your TV is a solid state device. It operates off of DC. Your microwave is basically solid state. It operates off of DC. All your electronic devices, if you got a digital clock, it operates off of DC. Right? You understand that? Everybody okay? So that means we have a desire, we got to have DC. We got to have direct current. So the first thing you learn here is you learn DC. Because solid state devices, electronic circuits operate off of DC. This device right here generates AC, but I can control it. But to generate AC, we have to start with what? With DC. And then I can regenerate it at what amplitudes and what frequency I want. Are we okay? Everybody okay? Direct current. So y'all all had DC. So in a direct current flow, the flow of current is in one direction. The electrons in the DC circuit flow from negative terminal to the positive terminal through the circuit and back to the positive terminal of the voltage supply. The voltage source never changes what? Polarity. Now, the big advantage of DC is we can do what? We can electronically control it. DC is produced by DC generators. It's produced by batteries. Batteries chemically. It's produced by devices called thermocouples. It's solar cells, which y'all familiar with. Piezoelectric devices. If you got a cigarette lighter that you hear that pop, that's a piezoelectric device. That's DC that it generates. We can do it with electronically through AC to DC converters, which is what you have in your car. So literally in your car, you don't have a DC generator, you have an AC generator. But your car operates off of DC. So what do we got? Well, we got a AC to DC converter in there. We call them power supplies that we'll look at. So this computer right here operates off of DC. Well, we plug it into AC. So it's got batteries in it, but then I've got what? I got this guy right here. What's this guy right there? On this side, it's what? AC. On this side, it's what? DC. And that's the function of that. So what this does, it allows me to power this electronic device off of DC, but I plug it into AC. So we call these power supplies. So there's one of these in your car. There's one of these in your TV. There's one of these in your microwave. There's one of these in your computer. There's one of these, that little old brick that we buy, the little box you buy that you get with your phone to charge it. That's what this is doing, right? You plug that into Alabama Power, and on the other side you get DC when you plug that USB cable. And of course bioelectric. Bioelectric is us. So we're bioelectric. Y'all understand that? What does that mean? We create electricity through biology. So with the chemicals in our body, we literally create electricity. That's what the metric is all about. So in the metrics, we're nothing but a bunch of what? Batteries. But we're living in a dream world. Right? So batteries, everybody's familiar with these guys. These do it chemically. This would be a DC generator. These are solar cells. Y'all are familiar with these guys. These are all over the place. A lot of our calculators and everything have solar cells on them. You see them on the side of the road, especially on the interstate when you're out where there's no power grid, and they've got the signs up there that light up at night, and you see a big old solar cell out there. Piezoelectric, these are these cigarette lighters and stuff like that. When you shock them they shock these piezoelectric crystals, they produce a DC. Thermocouples, we use these to accurately measure temperatures. So your oven's got a thermocouple. If you got a water heater, it's got a thermocouple in it. If it's a gas water heater. So these guys create electricity from heat. Solid state devices operate off of DC, but the power grid is what? AC. And we'll talk about why. The function of the first solid state devices that we're going to cover was figuring out how to convert what? AC over DC. So these are electronic devices right here. So the first thing we're going to do, of course, is figure out basically how these things right here work. And once you know how they work, then basically you can make your own, right? You understand that? And they're not hard to design, especially, we're going to teach a design called a linear power supply, which is real easy to design. It doesn't take much to do it and figure out. The math is not real complicated. These guys use what we call switching power supplies, and we'll explain the difference. But switching power supplies are real hard to design. So what we're going to do is we're going to deal with a solid state, and we're going to see how to convert AC to DC. Then we need to have a little introduction into AC. And we're talking about AC power. So the terms we'll look at is we'll look at something called a cycle, we'll look at frequency, we'll look at period, we'll talk about alternation. We need to understand RMS, peak, peak to peak, and DC average. Of course, we'll talk about the voltage source, and we'll talk a little bit about inductors, capacitors, and devices called transformers. I'm not sure I don't think we do that in this lecture, but we'll have to eventually get to those. So we okay. By the way, this version of the PowerPoint is not up there. I see a bunch of y'all trying to take these notes, but this will be up on Blackboard. So you can always go back and look at that, especially if I move faster than what you're taking notes. We had an instructor when I was in college. He would go over what was going to be he would go over the questions of the test, the class before the test, but he would do it so fast that if you took notes, there was no way in the world you could write them. So three of us got together and figured this out, that I would do this question, the next guy would do the next one, the next guy would do the next one, and we got it down. And then we'd get at the end and add the questions together. But yeah, he'd go over Mr. Martin. Alternating current constantly swaps directions. The voltage source in an AC circuit constantly swaps polarities, which causes the current to do what? Constantly reverse. So in AC, there's no such thing as positive and negative, because it swaps so fast that we consider AC not to have a polarity, because the swap is so fast. In fact, in 60, this is swapping 120 times a second. Which means it's swapping every 8.333 milliseconds. So basically, it's no polarity, right? The big advantage of AC is AC generators are a heck of a lot more cheaper than DC generators. So it's cheaper to generate. So that's why a long time ago, originally, the first generators, since the cars operated off of DC, they originally put a DC generator in your car. So if you get way, way back there, your generator's going to be DC. But once they came out with solid state and got the ability to convert AC into DC, they switched over to what? Alternators. And now we have a converter in there that converts. We call them a rectifier, by the way. We'll look at that. That does what? Converts AC to DC. Why did they go to alternators? Well, it's so much cheaper. You know, you might go out and buy, a 90 amp alternator. If you bought a 90 amp and you say, well, $120 something, that's you've got to add. If that was DC, it probably costs about $500. So it's a lot cheaper. Extremely efficient to transmit power. Transmission of power. It's a very, very efficient. So this is why we don't have, when they first came up with the power grid, Edison was a DC person, and they were trying to power up, I can't remember what city it was, but they had to have a power station every, I think, 4 blocks, because DC was very inefficient. How many of you live next to a power plant? How close? 10 miles. Gorgas? Yeah, but still, it's what? It's 10 miles. And why? Because it's not AC, it's what? I mean, it's not DC, it's AC. And we'll look at that in a minute. Voltages can be easily changed using transformers. DC and transformers don't get along. So we can change the level of the voltage real easy with these devices called transformers. AC motors are a lot less expensive per horsepower. So this is why originally DC had the big advantage of being able to control the speed and the torque precisely. But with the advent of solid state, eventually somebody figured out how to do it electronically. And of course, this is when these variable speed AC drives came up, and now they dominate. For a long time, that was DC motors. That was their calling in life, was when I needed speed control. Now it's going back over to AC. Why? Because AC motors are so much cheaper per horsepower. AC is produced by AC generators. It's produced electronically, which is what this guy right here does, and bioelectric. And I didn't know this until I started researching this years ago. So here's an alternator on your car. By the way, this is when they came up with in electricity, we call them DC generators and we call them AC generators. But the problem is when they first came out with cars, they called them generators. And they didn't put DC generators, they called them generators. And when they changed over to AC generators, they didn't want all these mechanics to get confused. So what did they do? They started calling them alternators. So they say your car has an alternator on it, and they say it's not a generator, but it is a generator. So the alternator on your car produces AC. If you got one of these guys right there, produces AC. These are some of the big generators at a power plant. They make AC. An electric eel produces both DC and AC. So it can produce up to 870 volts DC to kill something. And then it can do 10 volts AC at 25 cycles to stun things. So if it don't want to kill something, it can stun, which is pretty neat. DC AC inverters, we call these inverters. Some of y'all might have one of these you put on your car. Some cars put them inside. My wife's van's got one of these on there. So it's got a 110 volt outlet inside her van. So we can plug things in. Kids really like it because they can plug their phone chargers and stuff in without getting up front and getting to the USB port. And then, of course, electronically by a device called a function generator, which is what it is. So we'll be using these guys here during the term. Of course, I'm tapping on this and not showing it. This is the symbol that we use. So when we start playing around with electronics, the book, and I need to throw that in there. We have different ways we can draw things, and so we have to draw circuits. And one way we can do is draw what they call a pictorial diagram. And this is where you actually put the picture of everything in there, and you connect it with wires. If I was to do that with my stereo amplifier, either they'd have to make it smaller than I could see, or they'd have to make it so big it would fit up on an entire room, right? You understand? So we don't actually have pictures. When we get into these diagrams, we don't actually have pictures of the devices. We use symbols to represent the devices. So in DC, you learn some symbols. You learn the symbol for a DC voltage source, right? You know, it'd be awful if I for a car battery, I come up here and had to put a picture of a car battery up there, right? We learn symbols of a conductor, and you learn symbols for resistors. I think that's the only symbols you learned in DC. So we know what the symbol of a DC source looks like. This is a symbol for an AC voltage source right there. So it's basically a circle. It's no longer a group of dashed lines, one short, one long, like we do for a DC voltage source. This is the symbol for an AC voltage source. So it's a circle with this little squiggly line in the middle, and we'll understand this in here in a minute. You okay? And we've already, the alternating current is provided by voltage sources that swap watt polarities. This repetition will produce a voltage, and we're going to look at this at the next slide, which is pretty interesting. AC waveforms are referred to as sine waves because it varies with the trigonometric sign of the voltage, current, and power. And we'll look at that in a second too. So this is a sine wave. And it's generated on a circle. So it creates a constant waveform that goes up to a peak, drops down to 0, goes to a negative peak, comes back up to 0, goes up to a positive peak. So it's constantly changing direction. So it's got to go through 0. And how much current flow do we have when we got 0 volts? I is equal to V over R. 0 over any number is 0. So it has to stop and swap directions. You know, it'd be like driving your car. Can you change can you go between forward and reverse without stopping? Not unless you're a stunt driver and spinning around like that. I've seen these guys go, they'll be going backwards and they'll hit the brakes and spin it around. I can't do it, but they can. In AC, we can't do that. So AC is generated on a circle. You know, what we're doing is we're taking a parallel and putting it and showing the AC that's being generated for each place around the circle. And we'll look at that in a minute. So since if we call this 0 degrees and it makes one loop, then how many degrees in a circle? 360. So one one cycle or one waveform is generated every 360 degrees of rotation. Y'all understand that? Yes or no? When it's up here, we get peak output voltage. When it's down here, we get zero. It says, notice that one complete AC waveform, which we call a cycle, is generated every 360 degrees rotation around the circle. Are you okay? Zero volts is generated every time the radius of the circle crosses the horizontal plane. We okay there? That makes sense? Peak voltage, which we refer to as V peak, occurs at 90 degrees and occurs at 270 degrees. So if we call this zero, then this would be 180 degrees. So 180 degrees at 0 degrees and 180 degrees, we get 0 volts. At 90 degrees, and 270 degrees, we get peak voltage. One of them's going to be a positive peak, the other's going to be a negative peak, right? But they're going to be identical to each other. So if this peak voltage is equal to 100 volts positive, then this voltage is going to be 100 volts negative. So the negative peak, or what we call alternation, is the mirror image of the positive for this waveform here. And we call this what we call a sine wave. Now this is what Alabama Power is generating. So if we could actually visually look at it with something that allows us to visually look at voltage, not measure with a meter, but visually look at the voltage, then we will see this. And that's what this guy does right here. So this guy's called an oscilloscope, visually shows us the voltage. It shows us exactly what's going on. Your meter is not going to show you that. Your meter is going to measure a quantity, right? Everybody okay? I don't know where I got this in. This is not my animation, but it's really, really neat. So we pick up some terms. So we've got a repetitive waveform. So how long is this repeating? It's all the time. I mean, it's cycle after cycle, it's 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 after cycle. You know, that would be like years, you know, years. How often does years repeat? Every year, right? How often does second repeat? Every second. You know, how often does a day repeat? Every 24 hours, right? You understand? So 12 midnight is two things. What's 12 midnight? Well, it's the ending of one day, but it's the beginning of the next. And that's the same thing true with 0 degrees. So 0 degrees of one cycle is 360 degrees of the previous cycle. And this is just over and over and over. Every time the power's on. Right now, this light plugged in, seeing this, and it's seeing 60 of these every second. 60 cycles, not alternations. So we refer to one repetition. So this is a repetitive waveform, right? You understand that? And so we call one repetition of a waveform, we refer to this as a what? A cycle, which you should be familiar with that term. We talk about things running in cycles, which means once they're through, they cycle again, right? And do the same thing. So everybody okay on cycle? So here's something. So a cycle, one repetition of a sine wave, 360 electric degrees. Well, this is not exactly true. A cycle is one repetition of a repetitive waveform. So we got different repetitive waveforms. We'll look at the end of this class that are not sine waves. Sine waves is just the way power is generated. Sound waves is what I'm doing right now. These are sine waves. It's just they look kind of strange because they're all grouped together. If you ever played a guitar and had a microphone and clicked a chord and looked at it with an oscilloscope, you would see a sine wave. If you come up and hit a bunch of them and play a chord, not a note, you play a chord, they would all be composited or added together, and that's what I'm doing right now when I talk. But if you just pick one chord, you would see a sine wave. Alternation, each half of a sine wave. So we have a positive alternation and we have a negative alternation. The positive and negative alternations are mirror images of each other. So that means they take this exact same amount of time. If I'm spinning a circle at the same speed, right, you understand they'll take exactly the same amount of time. They give us the same amount amplitude. Now, if we do this electrically, this would be one cycle, this would be the next cycle, and then the next cycle would be out here, and the next cycle would be out there, and the next cycle would be out there, right? So you understand? Okay. This would be 0 degrees, but it would be what? It would be 360 degrees of the previous one. Then this would be 90 degrees. This would be 180 degrees. This would be what? 270 degrees. This would be 360 of this one, but it would be what? 0 of the next one. It's just like 12 midnight is the end of one day and the what? The beginning of the next. Now, frequency is the rate that the waveform changes. So it's one repetition. It's the rate of the cycles. So Alabama Power generates 60 cycles per second, which means if I could look at that, it would be every 16.77777 milliseconds that this thing here would be one cycle. One alternation would be 8.33333333 milliseconds. Now your meter don't show you that, but guess what? This guy right here does. So not what an oscilloscope does, it shows you voltage relative to time. So we can measure two things with an oscilloscope. We can measure voltage and we can measure what? Time. By the way, I keep forgetting his first name, but I think it was Ferdinand, I think. But just like in any science, people who are fundamental in developing the science usually get their name, they're honored with having their name used inside that technology. So cycles, normally when we talk about cycles per second, we use the term hertz. So you'll hear Alabama Power is 60 hertz. But as soon as I say hertz, what does hertz stand for? Cycles per second. So Alabama Power is 60 hertz. Most of our hemisphere is 60 hertz. The two main power frequencies that are used are 60 hertz and 50 hertz. If you go over in Europe and over in there, it's 50 hertz. Over here, it's 60 hertz. Now, the period is the time it takes per cycle. So if I had 60 cycles per second, then how long would one cycle take? It would take 1/60th of a second. It's going to be milli, but this is in a fraction. So it's one over the frequency. 60 cycles in a second, right? You understand? So that's like say if I do things at the exact pace, and I say I do 10 things in an hour. How long does it take me to do one thing? Well, it's going to take 1/10 of an hour, right? You understand that? Does that make sense? Well, I'm saying I'm doing 60 cycles in 1 second. So how long would one take? It would take 1/60th of a second. And of course, normally we would do this, which would be 16.6666. Most of the time people say 16.7 or 16.67 milliseconds because that's a repeating fraction. It'll go on forever. So we call this taking the reciprocal. Y'all know what taking the reciprocal does? It gives you the inverse of the number. It changes everything around. So I could say, what would be the inverse of 25? Right, you understand? What would that be? That would be this. Okay, do that on your calculator. And by the way, we do this reciprocal. We get the inverse all the time. So we have a reciprocal key on our calculator. So somewhere on your calculator, you have a 1 over x, or you have x to the minus 1. Anytime you raise the number to a minus 1, you get the reciprocal. So we do this inverse so often that instead of saying 1 divided by 25, we can come over here and do what? I can come on my calculator, and if you got a scientific calculator, I guarantee you it's on there somewhere. So this is the Windows calculator, and it's on here somewhere. So there it is right there, 1 over x. So that would give me the reciprocal. So instead of me coming over here and say 1 divided by 25 equals, right, you understand? I can come over here and say hit 25 and hit that key, and I get the same answer. Now, what's going to happen when I hit the reciprocal key again? Huh? It's going to give me the opposite of this fraction. Well, what's the opposite of this fraction? 25. You understand that? Yes or no? Okay. So that means if I know the frequency, I can take the reciprocal of the frequency to give me the period. If I know the period, I can take the reciprocal of the period and get the frequency, because they're the inverse of each other. So if frequency goes up, what happens to the period? So if I'm doing 60 things a second, and I'm doing 120 things a second, if I go to 120, it means the period's got to go down, right? So if frequency goes up, it's the inverse, right? You understand that? So if frequency goes up, what happens to period? Yeah, if I'm doing more things per second, then each thing I'm doing per second has to take less time. So if the frequency goes up, period goes down by the same ratio. If I double the frequency, I half the period. If I half the period, I double the frequency. So what we're saying is if I can measure the period, I can calculate the frequency, or if I know the frequency, I can calculate the period. Your new scopes, by the way, the scopes we're going to be dealing with, these are computers. So they can do this math for you. Your older oscilloscopes, all they did was measure time. So, but if I can measure time, I can measure the time and then take the reciprocal of that, and that would give me the what? That would give me the period. So older scopes, you had to calculate the period. New scopes will do the math for you because they're computers anyway. But we're not going to let y'all use that feature. We're going to get you used to doing this. Are we okay? Any questions? AC waveforms in degrees. So we call this angle right here. We call this the angle theta. Now this is not really important for this class when you take AC. All we're going to do is show you why this thing is called a sine wave. So what we're doing now, I wouldn't even worry about it. Okay. But why is it called a sine wave? Well, the problem is it varies according to what we call the trigonometric sign of the angle. And this is what we're talking about. A lot of people, you say, okay, if this is 90 degrees, and this is 0 degrees, and this is 10 volts, where would 5 volts be at? Huh? Well, most people think it's 45 degrees. And that would be true if it was a linear waveform. Y'all know what linear is? What does linear mean when we talk about the term linear? Anybody know? Y'all heard the term before and don't know what it means? Linear means it's in a straight line. So it means everything varies in a straight line. Is this a straight line? No. So it's not linear. So sine waves are non-linear. We have what we call a triangle wave, which is a linear waveform. And you could say, okay, with a triangle wave, it would be at 45 degrees. But with a sine wave, it's non-linear, so half voltage is not going to be at 45 degrees. Half voltage is up here somewhere. And that's, when you look at the actual wheel that it's spinning around, here's 45 degrees right here. I'm sorry. Here's 45 degrees right here. And look where it's at. Is that half? No, that's about 70.07%. Exactly. Where does half occur? It occurs right here, which is what? 30 degrees. So at 30 degrees, it's one half up. Not 45 because it's nonlinear. It starts off going almost straight up, and then as it goes up, notice it varies as it goes up. So 30 degrees is when we get to half volts. Now, what they figured out is that this varies with this is 0 volts. This is the amplitude at that point. This is V peak. So notice what it creates. So if I wanted a voltage, this is what I'm measuring right here. I'm measuring that voltage right there. And that's the instantaneous voltage of the waveform. From 0 up to there. So this is showing me that this point right here is equal to that line right there. It's not equal to this one, which is V peak. It's equal to that line right there. Okay, y'all understand that? So if I wanted to calculate this, if I could calculate the length of that line right there, that would give me the instantaneous voltage of that. Now I know the length of this. The length of this is this guy right here, which is V peak, right? You understand? So this is what we're generating right here. So this is my V peak occurring at an angle. This is the opposite, and this is the adjacent, and that is, so this, when we talk about the opposite and adjacent, we're talking about relative to this angle right here, which is in the center. Hypotenuse, which is the longest side of a right triangle, right? The opposite is the side opposite of the angle that we're dealing with, and then the adjacent. Now, I'm not going to give you the formulas, but we can calculate the length of this side if I know the length of this, which would be equal to V peak. So the hypotenuse is V peak. So if I say 10 volts V peak, then that would be the peak voltage, right? The opposite side is going to be the instantaneous voltage. So in trig, what we do, the trigonometric equation is the opposite is equal to the hypotenuse times the sine of the angle theta. Since the instantaneous voltage waveform varies with the sine of the angle, we call these guys what? Sine waves. And we can do that. So let's say this is 10 volts. This right here is 10 volts. So that's a magnitude, right? You understand? And let's say this angle right here is 45 degrees. Well, if I wanted to calculate this side right here, then I would say the opposite is equal to what? 10 times the sine of 45 degrees. So this is your scientific calculator. Here's the watt. There's the sine. See that? So I'd say 10 times, I might have to do this backwards. We'll say 45 sine equals 7.07 volts. Which I tell you, I said 0.707. That's a number that's going to come into play. If I say 10 times the sine of 30 degrees, look at the sine of 30 degrees, it's 0.5. So that's exactly half. Let's say 90 degrees. So I'd say 10. Now 90 degrees is supposed to come up and be 10, right? You understand? So I say 10 times the sine of 90 degrees. And what's the sine of 90 degrees? 1, 10. Let's say 180 degrees. So 180 degrees should be 0. So I'm going to say 10 times the sine. I'm going to say 180. I'm going to hit the sine of that. What's the sine of 180? 0. Now, 270 should be minus 10, right? So I'm going to say 10, right, times 270. I'm going to hit the sign of 270 as a minus 1. It would be a minus 10. So what we're saying is that AC output varies with the sign of theta. So you can calculate the instantaneous voltage anywhere on the sine wave. All you got to do is know the angle and know VP. And that, since it does that, it's called a what waveform? It's called a sine wave. That's why I got the name. Is it a linear waveform? No, it's not. So that 0.707, by the way, is going to come in quite often. But that is the sine of 45 degrees, which is 1/2 of 90, right? And that's what we're getting into here. We didn't talk about radians, but when we deal with lengths, so we looked at degrees, but when we deal with lengths, we deal with something called radians. And radians is, we're not going to talk about it, but basically the formula for radians is every circle has what, 360 degrees, but it also has what we call 2 pi times the radius. Now the difference between this is when we're actually talking about lengths. This is when we're talking about a displacement. So in a lot of our AC formulas, when you take AC formulas, we're going to get this guy in there a lot. Because when I'm dealing with values, I'm dealing with radians. Y'all understand that? And you got to be real careful on your calculator, because when you're dealing with angles, you have the ability to display them in radians, or you have the ability to display them in degrees. A radian is a length. So this would be a degree. So this would be at 90 degrees. But when I start talking about this right here, I'm talking about lengths, so I would deal with radians. Okay, that's the big difference. So that would be like a circle has 360 degrees. But when I say the circumference, I'm talking about the circumference being so long, then I'm only dealing with radians, which is a big difference. So what we do when we calculate DC averages, we're trying to figure out the average of this value, not angles. We're trying to figure out the average. So we're going to do something with the radian formula. We're going to transpose it. And so if I was going to try to figure out the DC average of that, that is the formula right there. 2V peak over pi. Now, where that came from? It came from radians. It came from this formula right here. So that means if I came over here and this was 10 volts, and I had the ability to measure that DC average right there, then I would come up and I would say, okay, that would be the average voltage for that would be what? 20 to VP divided by what? 3.14. In fact, I would use 3.14. If you use the pi key on your calculator, you're a heck of a lot more accurate than you need to be. So what would this guy? Anybody got their calculator? You gotta have your calculator in this class, guys. Huh? What is it? I'm waiting. So that means if I put a DC meter on this and could measure that one alternation, it would measure 6.37 volts. Now, the book teaches this right here. Now, how they get that is they split this up and change this to 2 pi times VP. If you take 2 and divide it by pi, you come up and get that magic number right there. So a lot of people learn that number. I like to use 2V peak over pi because it just sounds neat. Now, what would be the average of this? So this is going to be a plus 6.37 volts. This is going to be a minus 0.637 volts DC average. What would be the average of that? Huh? So how do we do averages? Well, I do averages by, so an average, I take my quantities. So here I would say 637, right? You understand? Plus a minus 637. and my average would be a what? 0. So guys, this is pretty dangerous. And so if you put your meter on DC and you put it in an AC wall outlet, it's going to measure the DC average of a sine wave. And what's the DC average of a sine wave? 0. Y'all want to see that? That we'll be dealing with. These are usually referred to as digital waveforms. And these are DC, but they pulse at a frequency too. So any repetitive waveform can be represented in a frequency. And you probably notice that, you know, when they start talking about processors and stuff like that, how fast they run and stuff like that. Well, that's not AC, that's a DC. It's running off these pulses, these pulse strings. We call them digital clocks. Of course, this would be AC. And so we can put digital wave. So here we still have VP, but the average and everything that we looked at, DC average don't come into play for these waveforms. Here, this is what we call a triangle waveform. It'd be pretty obvious why it's got that name, right? So this is one of the waveforms that we'll look at. So a function generator, the purpose of a function generator, we bring AC in and then we convert it to DC. And what can we do with DC? We can electronically control it, which means we can regenerate an AC. But once I regenerate that AC, then it don't have to be a sine wave. It could be a triangle wave. It could be a sawtooth, which is one that we'll look at next. But it's going to be AC, and we'll look at that. So that's some of the waveforms we can get that we run into. This is imposing a signal on DC, and we'll talk about this more often, more later, and where we can take an AC signal and superimpose it on DC. This is a waveform called a sawtooth. Can you see how I got that name? These are the basic waveforms that basically all waveforms are made up of, which is pretty neat. Like square waves are nothing but thousands of sine waves. It's really neat. We talk about what we call harmonics. So these are your basic waveforms that you'll run into. So we got pulse waveforms, we got sine waves, pulse waveforms, triangle waves, and then sawtooth, right? So these function generators, if you look at the thing up here, it has the ability to do all those. Now, what we run into is what can our meter use? Let me see where this is at. This is what's important. I'm missing something, guys. Something's missing out of my PowerPoint that I thought was in here. And we'll get this out of the way before class gets out. I didn't want to do that. And the slide's supposed to be here. I'll make sure it gets put into the version that's up on the internet. Is that we have a problem trying to do averages. So we know if we tried to average a sine wave, we would always come up and get what? 0. Y'all understand that? So that means, but when I come up here and look and see what's going on, we see that it can't be 0, because if it was 0, we would have absolutely no work, right? And I don't know where my inserted slide went. So they had to come up with a method that I could use to come up with, we don't call it an average, we call it an effective voltage. What effect does this sine wave have? So what they did, one thing we had to do is, so we got this sine wave, and mine's not going to be as pretty as the ones over there. And when we do an average, what I would do is I would come over here and I would take an average over here, and then I would take measurements at equally spaces. So if these over here was every 1 degree, then I would do 1 degree all the way around that. And if I averaged that out, I would come up and get 0, because my negatives would cancel out my positives. So what they did is they came up with a method to figure out the effects a voltage would have when the negatives didn't cancel out the positives. And the first thing they did was they squared all these things. So if you had your calculator and you had a -1 and you squared it, it would turn into a positive. So automatically it would change the sign to everything would be changed to a positive by taking this, by squaring this. So if I took all these guys right here and squared all these, then the negatives would no longer cancel out. Then I would take the average of the square. So what we would do is we would take the total, and then we divide it by the number. Right? Then what I do, now my answer is wrong because now it's a lot bigger than it's what's supposed to be. By the way, another name for average is the mean. You ever heard of that? The mean, that's the same as an average. And then what would I do is I would take the square root of my answer. And then that would give me the effective voltage. So this became known as the roots of the means of the squares. And we refer to this as RMS. You ever heard of that? Root mean square. That's what it stands for. Root of the means of the squares. So if I took the RMS of a sine wave, so that means a bunch on my positive and equally spaced on my negative, and I squared all those, automatically squared everything, then the negatives would be gone, right? You understand? Then I would average those squares. And then when I got through, I would take the square root of the mean, and then that would give me the effects of that. And this is called RMS. Now, if it is a sine wave, this will always be the sine of 45 degrees, or 0.707 times dp. Always. So, the effective voltage, this is not an average, this is an effective voltage. It's always, if it's a sine wave, it's always equal to Vp times 0.707. Always. So it would be very it would take a computer to calculate RMS. But why do it? Why do it if it's always what? Equal to Vp times 0.707. So for years and years and years, when I flip my meter on AC, it just takes that back, it takes Vp and does what? Multiplies it by 0.707. And this is a standard meter. But the problem is we get into waveforms that are not sine waves. And if I get into waveforms that are not sine waves, this meter right here would measure it wrong. Because this right here would multiply it by 0.707, and that only works for what? A sine wave. A sine wave is a nice symmetrical waveform. So if I'm working with stuff that actually requires me to know exactly what's there, then we buy what we call a true RMS meter. A true RMS meter is a computer. And it literally does what? Calculates it'll measure any ACC. Whether it's a triangle wave, whether it's a pulse waveform, whether it's the output of a variable frequency drive, and that's where we get into problems. Variable frequency drives are not sine waves. If I use a standard meter to measure the output of a variable frequency drive, it is not going to give me a true reading. So if I'm going to work on anything like that, then I need to do what? I need to buy a true RMS meter. True RMS meters cost about twice what the equivalent of standard meter costs. If you're going to work in electronics, if you're going to work in electrical, then you don't need a true RMS meter. It's like you going out buying a 1,000-watt amplifier and keep your volume turned down at 1%. It's just like going out and buying a cell phone that's got all these features and all you do is look at Facebook. All you did is wasted a bunch of money so you can brag about it, right? So true RMS meters are great. If you're in a situation where you're going to measure AC signals that are not sine waves, then you need a true RMS meter. If you're not in that situation, then you need just to buy a meter that uses 0.707. But 0.707 only works with sine waves. Sine waves are nice and symmetrical. This guy right here is a mirror image of that right there, and it'll always end up to be the sine of 45 degrees, which is easy to remember because that's 1/2 of 90, right? You understand? So V peak times 0.707, regular meters. RMS costs quite a bit more money, so now y'all know the difference between a true RMS meter and a standard meter. This doesn't make any sense buying a true RMS meter if you're not going to measure, be into the equipment you need it in. So that's what RMS means. So when you take a measurement with a meter, it is measuring RMS. So if I was to actually look at this waveform right here, this right here, this V peak right here is going to be on the magnitude of 170 volts. This down here is going to be about 170 volts. But the RMS value of this is 120 volts. And 120 is the work you're getting. Because it's only at this for a heartbeat. Then it comes down to 0. Then it comes up here. So what happens is your devices are seeing this effective voltage. They're not seeing peak. They're not seeing peak to peak. They're not seeing this 340 volts peak to peak. They're seeing 120 volts. So RMS, the way it came into play, if you run 120 volts RMS into a resistor, you get exactly the same work that you get if you have 120 volts DC. Exactly the same work. So but it's not called an average voltage, it's called a what? It's called an effective voltage, because it is not an average. So that's RMS. Y'all know the difference now, right? Now, when we start dealing with DC power supplies, we're going to be dealing with peak. So we need to know peak. But then, of course, we need to know what our meters read. So standard meters read RMS. If I had a true RMS meter and put it on that outlet right there, and I took this meter and put it on the outlet, it'd measure exactly the same thing. So my $200 meter and my $100 meter measure exactly the same thing because it's looking at a watt. It's looking at a sine wave. If I had a variable frequency drive or variable speed drive on an AC motor, and I looked at it with this meter and I looked at it with a true RMS meter, they would measure something different. And I would see it go up and go down, but I wouldn't actually see the true voltage that was there. So that's the difference. Y'all okay? So any questions there? So what did we go over today? We looked at, well, that's what this is talking about. These are some of the formulas they'll give you. I don't know if they're in the book or not, but I like to use this formula right here. Now remember, if we take the reciprocal of 0.707, if it's multiplication, it would turn it into division because it's the opposite, right? So some books teach this. So we could take V peak and divide it by 1.414, and we would get the same answer if we took V peak and multiplied it by what? 0.707. Does that make sense? We could go to V peak if we know RMS. If we know RMS, the way we go from RMS to V peak is we take VRMS, which is what our meters are going to read, and we divide it by 0.707. Or I could do what? Or I could multiply by 1.414. And both of those will give you exactly the same answer. Now the problem, why we need to know this is what an oscilloscope reads. So an oscilloscope reads peak to peak. And of course I don't like using this guy right here. This is the DC average, right? I like to use 2V peak over pi because it just sounds, to me, 2V peak over pi is easier to remember than 0.637. By the way, what I'll do is next class is I'll go ahead and give y'all out the formula sheet because there's a lot of formulas in here. All right, and just to understand it, knowing it is okay, but you know, to do the math you need formulas. But understanding that, you know, if I was to measure Alabama power, I'm going to measure a lot of voltage with an oscilloscope because what does an oscilloscope do? It shows you exactly what's there. What does this guy right here do? It don't show you what's there. It gives you an effective voltage, right? You understand? If you put it on DC, it gives you a DC average of what it sees. If you put it on AC, it's going to be 0.707 times whatever AC it sees. An oscilloscope, what's nice about an oscilloscope, it shows you exactly what's there. So we'll try to do that. I think I got a power cord around here somewhere and put it on the oscilloscope and let you see. It's almost 300, it's about 340 volts peak to peak to get 120 volts worth of work. Now, a lot of people says that's a waste, but what we find out we can do with AC that we can't do with DC is we can run it through a transformer. And what does a transformer do? Y'all know what it does? Well, it's either way. Yeah, we can step it up or we can step it down. So what we'll do next class is understand why do we generate power using AC and why do we use, of course, we know why we use DC because we can electronically control it, right? You understand? But why don't they generate DC? Why don't they transmit DC? So we got to go through the process now of once I get it to my house and I want to plug my TV in, that TV's got to have a power supply that does what? Takes that AC and steps it, takes it down, right? You understand, and then turns it into DC. It seems like it would be nicer if they could just do what? If they could just generate DC. Then we wouldn't have to have power supplies. And that would be impossible too. And we'll talk about that next class. Are you okay? Remember, let me double check that. Monday's a holiday, right? Oh, sure. Yes. Sometimes I get my calendar. Yeah, it's January 16th, Monday. So what's that mean? Yeah, so if you drive over here, you'll find the gates closed. So next class will be when? Wednesday. Y'all got two things you need to do, right? Before next class, you need to do the syllabus agreement, which you need to go ahead and do that anyway, because next class we have, but this weekend before Friday is what? Your quizzes and everything are due, right? Everybody okay?